Hello everyone. So today we're going to start on 8.4, which is the last section in chapter 8. So chapter 8.4 talk about three simple concept about vector field, and we call a vector field is what we are integrating over during a line integral. And one very basic interpretation of the vector field is simply think of it as a force field that as you learn in physics, like an electromagnetic field or gravitational field or things like that. So there are several important concepts about force field or vector field in general that we want to study, and they are flow lines, divergence, and curl. So some of these are very difficult to understand without seeing some kind of visual animation of it. And I think I mentioned in class that I'm also going to post a video link to a YouTube channel where it has some of these animation that can illustrate what some of these concepts are. But I'm also going to try to show you some picture that would illustrate that and hopefully help you understand when you watch the video and see the animation, it will make more sense also. So let's start with our first concept, which is called flow line. So what is a flow line? So before we talk about it, let's remind you the following. We call that a function vector f that map from Rn to Rn. And a function that map from Rn to Rn can be interpreted many different ways, but the interpretation that we're going to be using is this. A function f that map from Rn to Rn can be represented graphically as a vector field. So what is a vector field? Basically mean the following. Instead of trying to graph the input and the output all together into one massive position vector, we actually try to interpret the input to be a position vector. I'm just going to say position vector. And graphically representing them using dots. And the output, we're going to try to draw them as direction vectors. After all, this is what gradient vectors are. And one way to represent gradient of a function is to draw them as a vector field. And graphically, we'll represent them as arrows. So give you an example on how to generate a vector field, which you have learned back in chapter 5. Let's do this very simple example. Oops. Let's do it over here. We're going to let vector f of x, y equal to maybe something simple like this. X plus y, x minus y. I'm going to ask you to go and generate is vector field. And of course, I'm not asking you to generate a vector field throughout the entire plane. How about we just do the generate vector field over this region from -2 to 2 by -2 to 2. So meaning x go from -2 to 2 and y go from -2 to 2. So that technically generate about 25 points. So if you recall, when we do something like this, I usually ask you to generate a table. So I'm going to split this corner into x and y, x for horizontal value, y for vertical values. And for the x value, we're going to go from -2, -1, 0, 1, 2. Just simply doing the integer values. And for the y, remember what I told you guys, is that instead of putting the negative number on top and count down, kind of like what the x does, no, you label them the same way as how it would appear on the graph, where number on tops are the positive numbers. And then negative numbers are on the bottom. And that way, when you draw in your graph, you don't have to worry about getting confused. And I've been teaching this for over 15 years, and students who follow this rule, this suggestion, almost never draw the graph wrong. And students who don't follow this suggestion often get flip-flop some of their vectors because they have to mentally identify a point that's on top to be on the bottom, or a point that's on the bottom is on top. So please don't do that to yourself. All right, so let's try to generate a vector field. So important to understand is that each cell in this table is going to have a vector in it. And the vector is given by x plus y, x minus y. So let's go and do this. So x plus y would be 2, and x minus y would be negative 2. And x plus y would be 1, x minus y would be negative 1. And then 0, 0. And then negative 1, positive 1. And then negative 2, positive 2. So that's a nice simple pattern. X plus y would be negative 1 plus 2, which is 1. And then x minus y would be negative 1 minus 2, which is negative 3. And then x plus y would be negative 1 plus 1, which is 0. And negative 1 minus 1 is negative 2. X plus y would be negative 1 minus 0, well, plus 0, which is negative 1. And it will be negative 1 minus 0, which is negative 1. And I think kind of seen a pattern, so this will probably be negative 2, 0, and then negative 3, 1. Okay. And I also probably see a pattern across also. So this one probably going to be 0 and negative 4. And you can check that to see that that's the case. And then this would probably be negative 1, negative 3, negative 2, negative 2. And then negative 3, negative 1. And then negative 4, 0. And so this one, the top one will probably be 3, negative 1. And then 2, 0. And then negative 1, 1. I'm sorry, 1, 1. Which is 1 minus 0 and 1 plus 0. And then 0, 2. And then negative 1, 3. And then this one probably going to be 4, 0. And then 3, 1. And then 2, 2. And then 1, 3. And then 0, 4. So that's not too bad. And because of the way the function is, the vector field is x plus y, x minus y, which is basically a linear equation between x and y. It's follow a very nice simple pattern when you try to draw it out. So then let's go and try to draw this slope field. So remember what I mentioned to all of you when you're drawing a slope field is that you want to make sure you make rooms so that you can actually identify how big the vector is. But in practical drawing vector field, sometimes we artificially shorten the vectors because otherwise really long vector would actually overtake the graph and make the graph very messy. One common practice is that we'll draw all the vector the same length, which is unit length. But of course, then you're probably thinking like, well, then wouldn't we lost the idea of how like the magnitude of the vector, because that seems to be important. If we only drawing them all length 1, then we might as well draw a slope field or something, because that's basically what the slope field is. Slope field just indicate direction without magnitude. So but a vector does convey magnitude and direction, and therefore it seems arbitrary to just not ignore the magnitude of it. No, that's not what we're doing. Most picture that you see drawing a vector field would actually draw all the vector using a unit vector length 1, but would probably color code them in such a way to indicate that some particular color represent a vector that are longer or quote unquote stronger. So that way you can have a visual to see where the stronger vectors are or where the longer vector are without actually worry about it overtake the graph or confuse the graph. And you see that used often in textbook as well as whenever you try to draw a picture. But some cases in animation and things like that, you might actually see the vector being kind of the right length. But for us, I would like you to draw them in the right length for now, and just so that you understand that whenever you're drawing a vector field, you are actually concerned about both direction and magnitude of each vector that you draw. So what I'm going to do is first label the 25 points that that will be the input of our function. And if you have a graph paper, it will probably be best to do that on a graph paper. But unfortunately, I don't, so I'm just going to freehand this 25 point. Hopefully that I did a decent job. And now I'm going to try to draw the vector. So vector will going to be drawn as an arrow on each of these spots. So the first one is 4, 0. So basically it will go for the 4 unit this way. 3, -1 would actually go 3, but down 1. 2, -2 would probably be this one. And then 1, -3 would be this one. And then 0, -4 will be this one. Okay, as you can see, some of these vectors are probably going to overtake some of the other vector, overlap with some of the vector. For now, I'm going to be saying it's okay for now. This one would be 3, 1. So probably going to go to something like this. 2, 0. Probably like this. 1, -1 will probably be like this. 0, -2 will be like this. And then -1, -3 will probably be like this. 2, 2 will probably be like this one. 1, 1, 0, 0, -1, -1, -2, -2. And now the graph kind of have some symmetry now, I think. This one is 1, 3. So probably be 1, 2, 3. So probably over here. 0, 2. Go straight up by 2. -1, 1. It will probably be this one. -2, 0 will probably be this one. And -3, -1 will probably be this one. And then 0, 4 will be this one. -1, 3 would be this one. So you kind of have some symmetry to it. This one is -2, 2. -3, -1. -3, 1. So probably go to here. And then -4, 0 will probably go this way. So that's how the graph looked like. Now, it wasn't a really good graph. You really can't see how things are going. But at the very least, hopefully you understand the way the drawing a vector field is. Now, fortunately for us, we do have ways to actually generate some of these graphs very rapidly. And that would be using some kind of graphing device. So let me show you what this graph looked like if we were to actually kind of draw it out. So I think we did this one right here. Let's see, where did it show up? Oh, there you go, right here. All right, let me just try to move it. Oh, no, that's the wrong. That is. Okay, that is it. Okay, let me try to make it bigger for you to see. So this is how the field actually look like. So I don't know if you can see it, but it seemed to me that from our field, the graph would go curve down and then curve out. And then this side would kind of curve up and then slowly turn this way. So notice that these vectors are too long and overlapping. That's why hard for you to see. But once you actually artificially shorten it, then you would see that this is how the vector field actually look like. X plus y, x minus y, which is what we draw, I think. Yep, there you go. And now the interesting thing about it is the concept of float line. So if you look at this picture that's on the screen, you can definitely see that the arrows are kind of showing us which way we're supposed to move. As a matter of fact, one of the very common interpretation of what a vector field is to imagine that it describes the movement of water. Okay, imagine that you're looking at a body of water and this arrow kind of indicate which way you're going. Another way to kind of visualize this is also to imagine that each of these arrows represent direction of wind, which way the wind is blowing. So therefore, you definitely convey a sense of that you try to move along with it. And because of that, we can actually now try to trace out how the movements are. And when we do that, what we're doing is mathematically called the flow line. So what is a flow line? A flow line is actually this. I'm going to go and write a definition first, and then I'll show you what to draw some of this. Okay. A flow line is actually defined to be following. So before I give a definition, maybe I'll tell you what it is intuitively. When you're given a curve with the properties that at each point on the curve, the velocity at that point, the velocity vector at that point matches the vector given by the vector field. A curve with the property that at each point on the curve, the velocity vector at that point matches the vector from a vector field F. Then this curve is called a flow line of this vector field. So I'm trying to define the word flow line. So therefore implying that when you have a curve that kind of move in the same direction as what the vector field is showing, that's what we refer to as a flow line. And remember, the direction vector indicates the direction of the movement of the curve. So if it matches the vector field, that means they're floating along with the field. Now to show you some of them, we can definitely try to draw some of these directly on this vector field right here. And I can clearly see that if you start from somewhere over here, it will kind of go something like this. And if you're on the bottom here, you could do one of two things. Somewhere along here, you might end up moving this way. And then you might end up going this way. And then at the same time, at the top is the same way too. It might wind up curving out this way. So these lines are what we refer to as flow lines. Now, hopefully it might remind you of something that you learned in BC calculus. And that is what we call integral curve. However, important to understand is this. A flow line is not an integral curve. These two are very different things, even though they kind of serve the same purpose. Because if you probably remember learning it last year in BC Calculus, and you might remember that Mr. Ambrose or Mrs. Dillon might tell you, oh, when you draw the integral curve, just go with the flow, with the slope. And it seems like it's literally the exact same thing that we're doing here. Where I'm asking you to draw the flow line, you go with the flow, with the vectors. And that is true. However, these two things serve very different purposes. And that's the reason why a flow line is not the same as integral curve. Now, how is that different? So in order to understand the differences between them, you must first understand or recall what is an integral curve. An integral curve of a slope field is by definition the antiderivative of the differential equation that generate the slope field. So literally, in a literal sense, an integral curve is like the solution to a differential equation. Meaning that when you take the differential equation that generates a slope field and you somehow anti-differentiate it in some way, that's when you get the integral curve. It shows you the answer to what you're looking for. However, a flow line is not the same thing. The reason why, because a flow line cannot be the antiderivative of the vector f, of the vector field vector f. Why? Because if you think about it, if the vector field is indeed the derivative of some function, then you must recall the following. If f, that map from Rn to Rn, is quote-unquote the derivative of another function, then it implies our vector field f is a gradient. And therefore, once again, I'm using the word loosely, it's quote-unquote antiderivative, which actually we have a name for that, we call potential. Then quote-unquote is antiderivative is a function f that map from Rn to R. And notice that this type of function, f, generates a surface. And therefore cannot be a flow line. So therefore, unlike integral curve, which is the solution or quote-unquote antiderivative of the slope field, a flow line does not have that property and is not the same thing. Now, then you might be thinking or try to understand then what is a flow line? Well, flow line is the solution of something, just not the antiderivative of the vector field, but they are, technically speaking, solution to a system of differential equation. As a matter of fact, if for those of you at 11th grader who will be in my differential equation class next year, you will learn that they also refer to as trajectory of a system of differential equation. But I'm not going to get into too much detail of it because it is something that you will learn next year. Okay, so that's pretty neat. Now, something interesting about drawing this flow line is the following. Now, if you look at the flow line, notice that in this bottom regions, right here, flow lines seem to move away from each other. But, like in this regions, notice that the flow lines seem to kind of go toward each other. And that is an interesting properties about flow line. And so the idea is that is there some way to actually describe this behavior? And more importantly, is there some way to quantify this behavior into a numerical value that we can actually study? And maybe more importantly, do math with it. So the idea that we try to understand is how do the flow line behave? Why do they kind of converge to each other, and why do they sometimes diverge from each other? And that is the concept that I want to show you next, which is called divergence. So divergence is a description of a vector field. And the best way to actually understand how this works is to actually examine the flow line of a vector field. Oh, actually, you know what? Before I talk about this, I kind of have to give you a proper mathematical definition of what is a flow line. I totally forgot. So here's the definition. So definition is the following. Let's say given a vector field, vector F, vector capital F, or vector X, such that vector F map from Rn to Rn. Let G of t be the parameterization of a curve in Rn. So therefore, G map from R to Rn. The curve G of t is a flow line of vector f of x over the interval. So it doesn't have to be a full line for the entire curve, but if some part of it actually coincide with the slope field, then that part would be what we refer to as the flow line. So on the interval from a to b, if this is true, if g prime of t, that means the velocity vector, is the same as the vector given off by the vector field at the point of the curve. That's how we form the vector on the point of the curve, by forming a composition for each t in the interval. So that's the mathematical definition, is that when you take the derivative of the parameterization to form the velocity vector, and that the velocity vector actually matches the vector given out by the vector f at whatever point that you're doing it in, then that become a flow line. Now, maybe instead of talking about divergence, maybe I'll give you another example and draw you a few more flow lines just so that you can see how that works. So let's see what other picture do I have. This one actually pretty cool. Let's just look at this one. All right, where did it pop up? Did it load up all the way over here? Huh. Okay. Let's move it out here. And let's make it really big. Ooh, maybe a little too big. So this one is another vector field that I really enjoy. Is the equation in x squared minus y squared minus 4 for the vector, the first part of the vector, and then 2xy for the second vector. And I'm hoping that some of you can look at this and immediately tell me that what that kind of reminds you of. And I know when I look at this vector field, it reminds me more of a electromagnetic electromagnetic field, because it seemed to me that the arrow pointing out from one end and then loop around and connect and converge on a different end. So in this picture, you can kind of see that the flow line will probably be something like this. And then converges somewhere over here. And then you can have like maybe another one. And then another one. And of course, it also goes the other way. So these are what we call flow line. Now, one thing that's interesting about forming flow line is also indicated the direction of the flow. So I'm actually going to draw these little arrows to help me indicate that. I kind of did draw those arrows up here too, but I guess I probably should draw the arrow more like this on the curve so you can see better. Now, in this scenario right here, you can also see that flow lines somehow start from this somewhere over here, maybe a point in 1.75 maybe, and then it go outward and curve up and then curve back down toward maybe negative 1.75. And then this seems to be going around and around and around with a whole bunch of flow lines that's not parallel to each other, but kind of go in the same direction. Notice that the flow lines somehow start from this point, 1.75 maybe, and it diverge from each other. It moves away from each other, and then eventually they all start to move closer toward each other into this point, negative 1.75 maybe. Okay, so once again, that is the behavior that we want to describe. Is a behavior whether this flow line converges toward each other or diverges away from each other. And that, unfortunately, will have to be for tomorrow's or the next video. Okay, I'll talk to you guys in the next video. Okay, bye-bye.